last video, we looked at the characteristic polynomial and did an example of finding eigenvalues and eigenvectors for a matrix. One thing we noticed once we have an eigenvalue, we had tons of potential eigenvectors. We could choose any S and get a different one. So every eigenvalue has infinitely many eigenvectors. So to truly understand eigenvectors and truly understand the matrix, we need a bit more than just an eigenvector. We need to know what all eigenvectors together look like. So we're going to do just that. So once I have an eigenvalue, lambda, I'm going to look at all eigenvectors. I'm going to call it E sub lambda. And I'm going to take everything, every vector, on which A acts like multiplication by lambda. So AV equals lambda V. All of them, even the zero vector, I'm going to put them in a set, and we're calling that the eigenspace. The eigenspace, I want to say the eigenspace of A corresponding to lambda. Alright, so we know there are more than just one. In fact, we sort of found the eigenspace for a few cases. Turns out it's called an eigenspace because it's a subspace of Rn. So if I have an n by a matrix, it's going to be a subspace of Rn. We're going to prove it. We're going to prove the three properties as usual. So let's start. First property, what is it? The zero vector must be in it. Right, so this is the condition of membership in this set. I'm going to test it on V equal to 0 vector. So if I take A times 0, well, that's going to be 0. And if I take lambda times 0, that's going to be 0 as well. These are the same. So the vector 0 is indeed in E lambda. Second thing we need to prove that if I take two vectors that are in E lambda, I can add them and get a vector in E lambda as well. So let V W be in E lambda. Right, so let's write what we know about V and W. We know that A times V is lambda V, and we know A times W is lambda W. All right, so that was the condition for membership in this set. So as soon as we're told that V and W are in this eigenspace, we know that's true. Now we want to know that the sum of V and W is also an E lambda. So I'm going to look at what happens when I multiply A by the sum. We can distribute A. And get AV plus AW. Now we're going to replace AV and AW by what we found over here, what we know to be true. This is lambda V plus lambda W. And now I can factor lambda, the real number, out, and I get lambda V plus W. All right, so from here to here, we proved that V plus W deserves its membership in E lambda. And so it's a member of E lambda. That's the second property. The third one is that E lambda must be closed under scalar multiplication. And so I'm going to see what happens when I take V and stretch it by K. So I'm going to take V and E lambda, and I'm going to take K and R. E's in V lambda, so again, AV equals lambda V. But now I care about KV. So I'm going to test whether it has the right property, A times KV. Well, I can take the real number K and put it up front. So K, AV. AV is lambda V. Now V is a real number, so we could switch. Actually, let's switch to parentheses first, and then we could switch to real numbers. There you go. And so AKV is the same as lambda KV. And that means that, let me write it here. I'm sorry it's a bit low. That means that KV is in E lambda. Right, so I proved all three conditions. That means that E lambda is indeed a subspace of Rn.